Okay, so today I'm going to talk about how does the incremental compilation work in Scala, and also what adaptation did we need to do in Scala 3, and also what are some upcoming changes to it in the future, and maybe if you don't know about it, how can we make your build faster by organizing your code in a particular way. So yeah, I want to talk about first what happens when you're building your code in Scala. When you click like the run button or you do compile command in SBT or something like that. Then I'll talk about some of the ways that incremental compilation optimizes the speed of your build and any trade-offs that we might have to make when we do that. And yeah, what's the future and how can you optimize your build? So who am I? I'm Jamie Thompson. I work at the Scala Center, and the Scala Center is like so organization that supports the open source ecosystem and community for Scala. We're a non-profit organization, and I personally worked a lot on the Scala 3 compiler and some other tools. Currently, we are fundraising at the Scala Center. What that means is just like if you know somebody, yeah, so I don't know, if you know, if your company is using Scala a lot, or you know someone who works at a company where they use Scala a lot, just let them know that the Scala Center is looking for more partnerships. Right, so the purpose of what I'm saying to you today is basically that by understanding the Scala build at a high level, then you can make it better you can optimize your build. But remember this quote from Donald Knuth, which is that premature optimization is the root of all evil. It's a bit of a truncated quote, but basically it means, I'm going to talk a bit about performance and, if you do this, then maybe your performance will get quicker. So just keep in mind, don't obsess over these details because there's always trade-offs when you make a choice in optimizing for performance. So to give an example, let's say we have a sort of web service that's all inside one sort of project, and it has 50 source files that are all Scala files, and we have some library dependencies, about 10. And I'm using scala-italy to run this project, and it compiles and it's running. It's a web app. Now, there's several things that go into running the run command. So if I did scala run this directory, then first thing it does is it's going to fetch your dependencies, and it might run some source generators. For example, if you have like a protobuf protocol, it might generate some source files to implement that protocol. This happens once every time you change the configuration of the project. So that doesn't add much to the overall build time if you keep rebuilding. Then you're going to compile your source files to the Java class files, and this is the slowest part of the build. This is the part that we want to try and cut out as much as possible every time you rebuild the project. And then we're going to finally create the launcher and run it, which sort of happens whenever we have something that's called like a finished target code. So if you don't compile anything, you just reuse the previous compilation so you don't have to bundle again. And what does this compilation pipeline look like? So let's say we have our 50 source files, and they go into the beginning of the Scala pipeline, and you have your library dependencies in this sort of box, because it's like a bundle of things. And you're going to transform those files slowly throughout the compiler. And this is running in basically a single thread. And then you're going to produce sort of 200 artifacts at the end, which is going to be class files, which are the thing that run your code on the Java virtual machine. You have tasty files. These are things that contain signatures of all the definitions in your code. And this is used to basically type check against libraries. So when you download a library, you read the definitions in the tasty file, and that lets you use those definitions in your code. And then we might produce semantic DB, which is to do with text editors and going to definition, stuff like that. So when I built that code, it took about 15 seconds. And let's say I edit one line in that file. You would not want it to take 15 seconds again to build. Especially if you type an extra character, you wouldn't want that extra character to take 15 seconds. So it doesn't do that, of course, because we have incremental compilation in Scala. So in reality, a one-line change in a sort of in the top level of your application may only take less than 1 second to rebuild. To understand what incremental compilation is, we first have to understand what separate compilation is. And basically, yeah, separate compilation says like, given that I've compiled these files, these definitions exist, I'm going to reuse these compiled definitions to compile my next set of definitions. And it's the fundamental way that we build the library ecosystem in Scala. So just a quick example to say what does this mean. Let's just say you have the hello world program here. In this file, the only things that we have defined is this hello method. The compiler doesn't really know what this @main thing is, and it doesn't know what the print line thing is. These all have to come from a library somewhere. And yeah, so these libraries are all basically on the class path. So on the class path, we're going to have the standard library for Scala 3. We might have the classes that were produced from the previous time you ran the build, and we have the classes from all of your library dependencies. So incremental compilation says, yeah, let's use the products that were produced from the first compilation to then read those definitions and hopefully compile less things than were done before. So yeah, instead of running all of these files all over and over again every time you hit build, you're going to say, let's say you only changed A, then the compiler will track the changes of everything that depended on that A and only run those again. So we have theoretically saved 30%. We're only running 30% of all the files rather than all of them, so we're going to save some time. But in order to make incremental compilation efficient and useful, basically we need to obey two rules. It has to be correct, which means that it should only compile what it needed to compile. If we compile any more than necessary, then we're wasting time, and potentially it could be slower than just running the whole build. And it has to be performant to calculate the difference. So we have to, when we say, oh, we compiled A, then we track all the dependencies of what uses definitions from A. We have to make sure that's fast. Otherwise, could just be slower than running the whole build. So in Scala, we have a incremental compiler called Zinc. It's bundled with build tools such as SBT and Mill and scala-italy, probably more. And yeah, it's a compiler that maximizes the correctness and performance when calculating the incremental changes. And it uses this thing called the name hashing algorithm to detect changes. So this is a sort of diagram of how it works. We have the Scala compiler, which is the sort of red bar in the middle, and then it's wrapped inside of Zinc. So basically Zinc delegates to the Scala compiler. And then Zinc is talking to one of the build tools like scala-italy or SBT, and we get the request to compile these 50 files. Then the 50 files and library dependencies will actually go into Zinc because firstly, it basically checks its caches and says, oh, we haven't compiled anything yet, so we're going to actually compile these. And at the end, we produce these things, something called an analysis, which contains the analysis of the code you just compiled. And we have the classes. And once we've done that, then Zinc will return to the build tool and say, OK, we're done. And then let's say you edited one single file. Again, the build tool is going to say, compile all the 50 files. But actually, Zinc is going to read the analysis and say, oh, I've discovered that only A changed. So it's only going to pass A into the compiler again. And it will reuse the classes from the previous compilation. So feeding it back into the beginning. Then once we've done that, the analysis has changed, and we could detect that actually D and F use definitions from A, so they have to be recompiled again. And this is basically a loop that keeps continuing until no more changes are detected. And then we go back to the build tool and say, oh, actually, the compilation's done, we're fully done. And yeah, the goal of this big loop is to, even though we're potentially doing several compilations, in theory, it should be quicker than running like 1,000 files all from scratch. And now let's peek a bit under the hood. So the red line, you could say, is the Scala-3 compiler or something like that. And it's basically a pipeline of several modules that run one after the other over every file. And these modules are called phases. First, we have the parser, which reads the text from the text files into the compiler's data structure, which is called an abstract syntax tree. Then we run the typer, which checks that the code is actually correct and is a well-typed program. Then we run through this phase called pickler, which is the thing that produces these tasty files. So that records these signatures of the definitions and the method bodies and writes it all to a file so that when you publish your library to the internet, we have all the signatures published there. It's basically an efficient way of packing all the detail of the program into one file so you don't have to run the type checking and parsing all over again. Then eventually you go through all these other phases and you get to the backend, gen B code, which is the thing that produces the class files so you can actually run the program on the JVM. And yeah, once that's all done, you get the class files and tasty files at the very end. So what incremental compilation does is it modifies this pipeline to add 2 new phases in the pipeline. So this is the dependencies phase, which goes through all the trees in your program and checks out which other files did this file depend on. Did it use a definition from this other file? Did it use a definition from a library? We need to track that. And also we go through this thing called the API phase, which is another way of tracking the API of all the definitions in your code. So look at all the methods, all their signatures, all the arguments, all the classes, and it sends that representation to Zinc through the compiler callback. And then Zinc uses that representation of the API to do its analysis later. Okay, so basically when you send the dependencies in the API to the callback, then they end up in this analysis bin in the right. And yeah, collecting that adds a little bit of time to the compiler pipeline, about 10% of extra overhead. But remember that overhead is going to save you in the long run because every time you recompile, then you're going to compile less, only the changes. Okay. So what's inside this analysis? Basically, we have timestamps and hashes. These are used to say which files have changed. We don't know what changed about them, just that they changed, that they were updated at some point. Then we have the APIs, which is a simplified data structure that kind of represents the Scala type system, but it's just dumb. It's just trees. It doesn't really have any semantic information. Then we have the dependencies, which is like just saying this file, this class used this name somewhere. So we'll have a look at that. So I explained, stamps is when you say the file A changed on the file system, so let's recompile that. Then more interestingly, we have this APIs thing. So let's say you had the Z Scala file, and it has this class Z, and it has these definitions. So it has 3 overloads of foo, and it has 1 value bar. And then what in the APIs, we're going to have these name hashes. So all we're going to record is that Z is a class, and it has the name foo and the name bar. And these hashes are basically the combination of all the APIs that, so all those 3 overloads will have different signatures, and they all get merged together into 1 hash. So all we really care about is, did this hash change when you recompile? For example, let's say, yeah, you had class A has this val bar, and it has this def foo that returns string. If you change the name of bar to the other name, or change the result type of foo, then we're going to have different hashes, and we'll have to recompile the dependencies of those names. And then the dependencies is the dual to that. So we say, either class D inherited from class A, or we say class F used some name foo, and we don't even know where it came from. It just used a name called foo. And class F is also perhaps using any member from class A. So these dependencies seem very generic and very vague. The reason that they're so basic is that is enough to do a fast approximation. And the approximation is really all we need to capture the most, not too much, but not too little. And so we get the best algorithm for changes. So now I've explained all of that. Basically, you might ask a question like, should you try and optimize your build specifically to maximize this algorithm of focusing on just the few files that changed? And I say don't go overboard, like don't do 1 file for every single method, or make your classes really tiny so you can have a 1 file for each of these tiny classes. But if you do, in general, use smaller files, then basically you're going to make a more granular graph of all the dependencies between these files, so then we can compile less when things change. So if your project has like 1 million lines and everything's just in 1 file, please split that up. I mean, it will help you read the code, but also it can help you have a faster build. Yeah, so how do we, this basically what I described is the algorithm as it was in Scala 2. And in Scala 3, we had to do something to support incremental compilation. The good news is we basically used the exact same Zinc compiler. The only thing that we change is how we talk to the Zinc compiler from the Scala 3 compiler. So the challenge was basically, yeah, how do we make sure that we could continue to keep talking to Zinc? And when Scala 3 adds all these new features that Zinc doesn't really know about, how do we represent those inside of Zinc? Basically yeah, I don't know, this is a bit boring. I don't really need to talk about this. So yes, Scala 3, usually those Zinc phases, the API and the dependencies, they used to ship inside of SPT, but now we build them directly in Scala 3, and that lets us test them before we even release the new compiler. So that's a better win for maintainability. And yeah, we basically had to make a bunch of changes to approximate the API of the new Scala features. So inline definitions, they were not in Scala 2. So yeah, the thing that's special about an inline method is that basically the entire method is its signature, because if you change the body of the method, then you need to recompile all the dependencies of that. Previously, you could just ignore the right-hand side of a method because only the type, the return type mattered. But now with an inline definition, you need to track everything that changes. So basically what we do here is that we're going to do a hash at the method body so that we can still have a compact representation without having to store the entire inline method and all of its transitive inline calls into Zinc. We don't need to do that. We just hash it in the compiler and send that small hash in addition to the method arguments. Okay, so that was the changes that we added in Scala 3. Now I'm going to talk a little bit about when you have Scala projects that have multiple sub-projects. So the reason you might do this is because maybe you have the client and a server, as we saw today. These would need to be compiled in 2 separate projects because they basically run on different platforms. Or another way you could split them up is because you have some common core definitions or utilities in one library, and then you depend on them from several submodules. Why do you want to split this up? Again, it's going to help you improve your performance of the build. Yeah, basically you want to think of your application as a bunch of libraries that all work together. Why do we do this? So again, look at all these files. If we split them up into these logical units, then we consider them separately, and that means that we can compile them potentially in parallel, which saves time. So let's say I had that web service at the beginning. Now I'm going to split it up into the common, which is some utilities, and then the database module, the authorization module, the data models, they all depend on that, and then the server combines those things. And now we'll see why this is good for your build, because previously, remember this was all just in one module before, so it took this much time. So imagine that was all just one module of files that you'll have to go through, the compiler has to go through. If you turn on your multi-threading, if you have a multi-core computer like most people do, then when you actually build your project, now all these three things were on the same level in that dependency graph, so then they compile in parallel, and then you save time in your build. So yeah, somebody might see that and think, okay, now I'm going to make millions of modules, tiny little modules with one file each. So then I'll have like infinite parallelism. Yeah, you shouldn't do that. And I actually have some examples of projects where it doesn't really help if you do that. But yeah, in general, if you have one giant module, consider splitting it up into several modules, at least so that you can take advantage of multi-core processing when you build your project. But also, it's going to help you think about the project more because you clearly delineate, oh, this code is all self-isolated, and then this code depends on that. So it's just about modularity like you learn in school. But can we do even better than this parallel building with multi-threading turned on? And the answer is yes. So there's this sort of idea of a pipelined build. What is that? The idea is that if we have several projects that all depend on each other, can we make that downstream project start compiling before its upstream project has finished compiling? And this has been done before in the Scala world, notably by Morgan Stanley with their opt-obt build tool, which is in the process of being open sourced. And then Bloop, if you know about Bloop, it used to have pipelining built in, but that was removed because it was unmaintainable, but maybe we can bring it back. And SBT today does support pipelined builds. So, oh yeah, and I just opened a pull request in the Scala 3 repository to add support for pipeline builds, and I do have a demo. But yeah, so how does it work? Let's just say you have project C depends on project B depends on project A, and even on your multi-core processor, you have to wait for each one to finish compiling before you start the next one. So this is like the theoretical maximum speed without turning on pipelining. But if you do turn on pipelining, then yeah, project A is going to compile up to here. Then at some point it will say, I have the APIs, start compiling the next one. And then project B says, I have my APIs. And you basically multiply up that saved time to speed up your build. So how does this work? Let's have a look. So I have a small demo. I made this pretty useless application that is just like I'm using it for basically a fancy calculator for my bank statements. But yeah, so I have a utility project at the bottom. Then I have core that depends on that's better here. So I have a utility project at the bottom. Then I have core that depends on the utilities. Then I have this cleaning project, which just like implements a bunch of cleaners that read CSVs from all the different banks and merges them into a single data format. And then I have app that runs the code at the end. So I don't have pipelining turned on at the moment. So this is the magical key you need in SBT. I have pipelining turned off. And basically if I need to pay attention to this right-hand side here. So when I compile, we compile the utilities, then we compile the core, then we compile the cleaning, so it's very slow, and then we compile the app. So if I turn on the pipelining to be true, then I should be able to reload this. I'll just do that. And then I clean that. Then you need to pay attention in the right-hand side again, because when we compile, then we do the utility, and then we're doing cleaning at the same time, and then we're doing app, and it's way faster. Way faster. So that was like 5 seconds compared to 13 seconds. But remember remember, there's a bit of JIT warm-up between each of these runs, but you could see that is adding parallel when there wasn't before. So that's how that works, but it's still work in progress because I haven't proven that it's safe. Maybe there's still some concurrency bugs in there, but the speed, that's what we care about. I want to hear just speed, that's all that matters. So you saw that previously it was going like util, then core, then cleaning, then app, but then it's basically doing the downstream one as soon as possible, as soon as it possibly can. And when is that as soon as it possibly can? It's basically as soon as we've done the type checking and as soon as we've done the dependency checking, then we have all we need to send to Zinc to compile the next module. So this is what the scala-italy compiler looks like now, which is what I showed earlier. And what it's doing is basically when you run the pickling phase, then in a separate thread it's writing the tasties. And this is like wasted time, as you can see, because we want to start as soon as we have this tasty, but we've got to finish the class file outputs and stuff like that. And that's a lot of wasted time in my view. So with the changes to add the pipelining, what we did was we just swapped the pickler and the API phase. So that means that this tasty is happening in parallel with doing that API phase. And as soon as we finish that, then we send the tasty to Zinc, and then we can continue the downstream modules. And that does save a lot of time, as you just saw, so that's what we care about. What does this slide mean? Okay. I'm going to ignore that. I forgot what that means. Oh, yeah, so this is basically when we output the tasty, and it goes into this jar file that's like internal to SPT. No one really needs to know about this. It only contains tasty files. It doesn't have class files. So basically, the problem is we don't need to wait for class files. We can just use tasty to start the downstream compilation. Okay, so in June, on an earlier version of this pipelining, I did do some benchmarks on this computer, which is 2019 MacBook Pro. So yeah, it only has 16 gigabytes of RAM, so that's sort of maybe a bottleneck in some cases. Okay, so I compiled LeChess. LeChess is this chess website. I don't know if you know about it, but it is running all with Scala 3. And when I compiled this project, let's say here's what it was. What is it? Okay, so yeah, black was before. So when we compiled just with the standard compiler, basically it was slower, but used less memory. When I turned on the pipelining, it was quicker, but it used more memory. Why is that? Basically just when you do things in parallel, then you need more memory. So it's a trade-off again. We all love trade-offs. Yeah, so yeah, overall, I still got I didn't put percentage there. Yeah, it's about a 24% speed up with LeChess. I mean, that's pretty good. But I did do some more benchmarks. So I did do a bunch of more benchmarks. Scala-Dex, for example, 31% improves build time. Why is that? If you look at the structure of Scala-Dex, it basically has like at least 4 layers of these dependencies, which I showed you with that calculator app. The more levels of dependencies you have, the more telescoping, like the more you're going to increase the performance by pipelining. So we have like multiple things in parallel, multiple levels, so it's just going to maximize that speed up. But yeah, so this is what it looks like in the end. Saved some time. Yeah, so again, the question is like, am I going to super maximize my build to optimize for this pipelining? And no, you should not, because yeah, if you have way too many small projects, it's the same for what I said earlier about the multi-modules. It's just like, for example, you have the Guardian front end. This project has like, I don't know, 50 modules that are all compiled in parallel. So if you have, I guess, like a supercomputer in the cloud with 60 cores, this will be great for you, but my laptop only has 8, so what ends up happening is when I turn on the pipelining, you might expect like all of these are going to be shifted like here, and we're going to save some time. But really what happens is that there's so many threads starving that we just stop compiling this. We just stop compiling this, compile everything else, and then we finish compiling it after we already did all the downstream. So you've got to be careful about thread starvation. Okay, so is there even more improvements? Yes. We could do something called a 2-pass compilation. And I was trying to work on this last night, but it didn't manage to make a demo for you today. But yeah, so let's say this is your pipelined build. Theoretically, what we could do is we run just a first pass, which is running the type checking, the parsing, and then the pickling. And then we run again, but we use all the source files, but we turn them into batches that get split up across all the cores. And then we only run just the type checking phase, because that lets us track the dependencies. And then, yeah, then we, at this black line, then we say, oh, now we start the downstream dependencies. So you could theoretically get even more time saved there. But yeah, oh yeah, and sorry, I forgot. In this first pass, what we do is we skip the right-hand side of method bodies. So basically we just say, oh, it's just a method that returns int. I don't know what it does. And then that saves time because you don't need to look inside the method bodies. So I did do in the summer, in June, I did actually manage to get it to compile on the .e code base. And it did have 34% improved speed of compiling just that Scala 3 code base. So it went from 4,900 lines per second to 7,500 lines per second, which I think is quite a high speed for Scala compilation. Oh yeah, and that's all I did there. So yeah, I hope that people try out my pull requests. I don't know if you want to try it out. It'd definitely be good to try it out because I'm really not sure if there's any concurrency bugs if you like edit a file and then try and recompile. So maybe there's some problems there, but please try that out. And I'm done with that. So thank you. So any questions? Yes.
I don't know if you said something about it and I missed it, but how does this work with macro or macro-based code? Because as far as I know, code that produces macro can be fully compiled before using it in even referencing it in another project. So
yeah.
will it be forced to compile it completely before? Will it be able to know if there are macros in a specific project?
Yeah, that's a great question. And yeah, you're right. Maybe I can show this. In SBT, basically, when it decides should I compile the next project, it's going to look in those APIs and say, if I see a macro anywhere, then by default, I'll just treat it like a normal project. But what you can do instead is you can configure so that you can actually still compile a macro if you want. But what you should do is you have to put the macro implementation in a separate project. So let's say, yeah, I think is this one. So in the build, you're gonna use the pipelining, but then you want to put the actual macro implementation in a separate project. So this is the wrong one. No, this is the right one. I just opened the wrong file. Okay. So let's say, yeah, I just put the macro definition implementation in here. So this isn't the inline method, it's the implementation. And then in a downstream project, I can call that. And basically, yeah, so you put the macro definition here, and you turn export pipelining off. So this just runs like a normal build. But if you keep that really small, then it's going to just be a very small project, so it won't take so long. Then the project that actually defines these defines the inline methods that use that macro, then that could still be pipelined. And I added an extra setting to make sure that you can verify to yourself. It will like throw an error if it doesn't match the right configuration. So yeah, you can still do pipelining, but you have to separate the definition and implementation. Yeah. Yes.
Well, you were talking about the outline compiler and
yes.
the possible optimization using best on. Did you have a chance to measure the impact of type inference for return types on the signatures? So I suppose that it is lower if you want just the outline.
We could do it now, or I could get back to you at the end of the day.
I don't want to make it work necessary, but I was wondering because once you're talking about outlines, I suppose if you provide the return type yourself, you're saving a lot of work, but that's how instinct.
Yeah, I mean, on a very basic demo, which was just like a single file with a single definition, it was half the speed. That was a single file with a single definition. So
Intuitively, yes. Okay.
Intuitively, yes, it definitely does. So I can demonstrate it working. It's just it seems to be broken in some situations. So it wasn't really great for actual demo, like wow, this is amazing, you know. But I can at least show it working. In fact, we could try and compile the Scala-free compiler itself again with that thing. But yeah, I wanted to try it on Lichess, and I tried it last night, and then I had a bunch of errors, so I wasn't sure what that was. So I gave up.
And I suppose that will have an impact even without the class computation, have an impact.
Well, the problem is you don't want to use this outline compile unless you're using pipelining, because you're going to duplicate work. That wasn't the question, I guess.
No, but I get it. I mean, it wouldn't make sense to talk about outline compiler without pipelining anyways.
Yeah, right.
Why are you introducing outlines?
But was there another question in there? I might have skipped over it.
I was wondering whether adding or removing return types to public methods will have an impact regardless of the pipelining, even on a single project on a single company.
Oh, well, yeah, maybe just because type inference, you have to do a type inference, and that will add a bit of overhead, I guess. Definitely compared to what you do previously, if you just declare your return type explicitly, then all you have to do is just say, does this match this explicit return type? Yeah, so it definitely does speed it up. It's definitely a good recommendation to annotate all public definitions. Good catch. Yes, hello. Yeah, I mean, we could definitely add a mode that forces you to do it, because then, like, you're gonna, yeah, then you'll just save time with this outline. You think? Yeah. I think if you already use Scala fix, there's a mode in Scala fix where it forces you to add all the return types.
Yeah, but what I'm saying is that the language allows you to put them, you can speed up the type of
Only with this pipelining mode. Yeah. I mean, that's what we're doing. And when I turn on the outline mode, then I skip the method bodies. If there's an explicit result type. We have to run type checking twice. What happens is you pass the code, then you type check it in this outline mode. And then you run the pickler, which produces tasty files of just those outline tasty definitions. So we skip the bodies. And that's all you need to compile the downstream project. You just need the public types. Wow, this is compiled, so I don't know if we can actually try this out. Otherwise, if this doesn't work, then why can't I close this? I don't know, just do. Actually, how do I do that? I have to do it from, then I need to do the settings. Okay. I'm actually just improvising here. Then I need to go to this one. This probably won't work. Wow. No? Where? 300, okay. Yeah, this one, yeah. Thanks. Okay. This is just the build, right? It's not actually doing anything yet. Okay, then I'm gonna do. Then I'm gonna do Scala 3 compiler compile. Outline completion enabled. Yeah, I'm using 16 groups of parallelism. So this is 14 parallel backends. What I expect is the downstream project will fail. Yeah, so still something to fix there, but yeah, thanks for listening.